One rule of thumb that you're going to need to use this entire time is the idea of closer to fluorine the higher the electronegativity means more partially negative. So if you have two elements, the one that's closer to fluorine is going to get the negative, the other one will get the positive. That'll help you with the concept of polarity. Hi, welcome to section 6.5, what's called molecular geometry. In this one we'll be looking at the different shapes and determining how things are going to be polar or not polar. Make sure you answer these questions before moving forward. It kind of relates to the idea when we talk about bonds and attractions, as this is something students often get mixed up. So, you're going to want to have this to be pretty large in order for you to write on. It makes it easier to add to it. So if you have a little small page, you might want to make it a little bit larger going forward. So when we look at the idea of linear, making a straight line, it's kind of the general structure of this. There's generally no central atom. If there is, though, it would have 0 lone electrons, meaning pairs of electrons around the elemental symbol. Alright, so let's take a few Lewis dot structures for these. We could easily have something like hydrogen bonded to hydrogen, something like hydrogen bonded to chlorine, something like carbon dioxide, and again, Lewis structures show the dots of all of the electrons. But you can see they make a essentially straight line. Now how this is different in a 3D shape, the 3D shape only shows when the connections between the bonds. It doesn't show unshared electrons. This is something the book does not teach. But it shows the number of bonds between the different elements. Now as far as if these are polar or not, it's a maybe. It's conditional, as we say. So it's polar if there's different atoms without symmetry. So the idea, different atoms without symmetry, that they're not symmetrical, so this one would be polar. It's nonpolar if it's the same atom. So nonpolar, because hydrogen and hydrogen are the same. Now when it comes to carbon dioxide, we have to just look at the idea that it is symmetrical along this axis that we have here, as there's an oxygen on the right and an oxygen on the left. If we wanted to talk about polarity of partial negatives and positives, just take a little closer look. Oxygen is more electronegative when it comes to carbon. So carbon would be partially positive. And in this pairing, carbon would be partially positive. When you have something polar, there needs to be a positive end and a negative end. Over here with chlorine, partially negative, partially positive. Up here with hydrogen, we see there is none, so that's why it is not polar. So again, when we're talking about this, we have a partially positive side and a partially negative side. However, with this, we have kind of a positive center and a negative perimeter, if you want to use that right term. So that's why this is not polar, because there is no positive and negative end. That's a general rule when we think about what's called polarity. So let's look at our next more complicated area, bent. There are electrons around the central atom. Now, some example of Lewis structures. We have simply our water. Now, that is H2O. Lewis structures, again, might be written straight, might be written bent. It doesn't truly matter. But we can see that there are some lone electrons around the central atom. Lone electrons, lone electrons, lone electrons, or unshared electrons. And that's what's going to help make this bent and kind of push the other atoms downward away from it being straight across. So 3D structure would have it written as oxygen bonded with hydrogen, and we write it in a bent format to illustrate that it is not linear. And you know this because these extra electrons are pushing these down, keeping all of these other electrons as far apart as possible. Now when we think of polarity, the answer is yes, it is always polar. Because if we take a moment to evaluate the electronegativity with each of these, oxygen is partially negative, hydrogen partially positive in this pairing. The higher electronegativity makes it higher electronegative, which makes it negatively charged. So we can see that there is a negative area, and this would be a positive area. So that would make this polar. With this one over here, we have the idea that this is partially negative, this is partially positive. In this pairing with nitrogen and oxygen, this will be partially negative and this will be a little bit positive. Some of this right here will cancel out, but overall the idea is that it's still going to be a little bit more negative. So this would be a big negative area in the molecule, and this would be a positive area. So negative end, positive end. So this would also be polar. And because of the unequal geometry of a bent shape, no matter what anything is bonded to it, it will always be polar. Now let's look at our next one. Let's see. Trigonal planar. So it makes a triangle in the plane, meaning how it's flat. So there are no lone electrons around the central atom. So some examples of dot structures. A very common one that you'll see in the book is with boron. Boron happens to be stable with only 6 valence electrons. But one more that's a little bit more real is this one here, a organic substance. I think this is formaldehyde. But we see that there are no unshared pairs of electrons around the central atom. Everything is shared. Now because things are flat, we just indicate things that are within the same plane as being aligned. So boron, boron, and we would want to indicate that the atoms around the central atom are kind of the points in a triangle. Hence why we get the triangular planar. It's all in the same plane and it forms a triangle. Again, carbon here, oxygen double bonded, and then a hydrogen over here and a hydrogen over here. Again, if we want to talk about polarity, it depends. If we have different atoms around the central atom, it's going to be nonpolar. So this one would be nonpolar. However, if we have different atoms, it's going to be polar. And let's just take a look at why that's true. So with boron and hydrogen, boron in every case is going to be partially negative, while each of the hydrogens are going to be partially positive. So again, this gives a kind of negative core or negative center and a positive perimeter. For something to be polar, it has to have a positive end and a negative end, which this does not have. However, when we look at this part here, this is partially positive, while the carbon being more electronegative will be partially negative. And in this case, we have partially negative oxygen because carbon is less electronegative. So again, here we see we could even take the idea that these will cancel out. But in the end, we have a partially negative area on top and a partially positive area on the bottom. We have a negative end and a positive end. And that's again why it's polar. Let's take a look at our next shape we have here. Trigonal pyramidal. So there are lone electrons around the central atom. And what that means is unshared electrons. Now this is going to make a triangular pyramid. So let's look at a few examples as far as dot structures. Ammonia, or NH3, is a very common one. As is phosphorus with some chlorines. And remember, dot structures do not have to follow the shape of what we're looking at. They just show the bonds and where all the electrons are. Now the three-dimensional shape, we finally get into something a little bit different. Because this is making a three-dimensional shape in multiple planes, we have to treat this a little bit differently. So in order to draw this 3D shape, we have our nitrogen and we have our hydrogens kind of placed like this. Now let's say the two hydrogens on the outside are kind of like the two base corners in a pyramid. So we're going to draw this almost like a little three-dimensional ramp, illustrating that we have in perspective the hydrogens coming towards you. Now this hydrogen in the center is the back corner that is now behind the nitrogen. We usually do a dashed line, but that indicates something else in science. So we're going to do kind of these lines across, indicating a bond, just like the ramp, only it's behind the nitrogen. Please ask in class so I can show you a model of what this one looks like. The same also is true for the phosphorus. We have the chlorines like this, to where one chlorine is coming towards you, is closer to you than the phosphorus, as is this one. Kind of just color those in. And the chlorine that appears to be in the center is behind the phosphorus and the other chlorines. It's pointed backwards, kind of into the page, while the chlorines with the black triangles are pointed towards the plane. Now this would always indicate that these things would be polar, because when we think of partial negatives and positives, all of the ones for the nitrogen and hydrogen are going to be partially negative on top and partially positive on the bottom, again giving a end and another part to it. And again, the chlorines, these are partially negative. Oops. These are partially negative, while the phosphorus is partially positive when compared to all of these negatives. So again, we have a positive end, negative end. That's why it's always polar. Negative end, positive end. And again, all you need to do is look at the electronegativity and seeing which one is further from fluorine. Further from fluorine means it's means it's less electronegative. Closer to fluorine means more electronegative. Now we're going to get down to the last one. It's called tetrahedral. Again, no lone pairs of electrons around the central atom. Looking at a few. So something as simple as methane, CH4, and something like even carbon with, say, just a couple chlorines. And hydrogens. So again, everything is bonded around the central atom. And when we say tetrahedral, tetra means four, so there's 4 atoms around that central atom itself. So the 3D structures for these will look very similar to the trigonal pyramidal. When we have carbon, and we have one hydrogen that's within the plane, so we can use a line. And then again, we're going to have these triangles indicating these hydrogens coming towards you, and then one hydrogen going behind. And so it's again making the kind of 4 corners of a pyramid with the carbon in the center. Again, say I have a chlorine here, and one chlorine on this side, one hydrogen going back, and one hydrogen coming towards us. Now, when we talk about if it's going to be polar or not, it's conditional, it's maybe. If you have different atoms around there, to where everything's not just the same one, it's going to be polar. While if it's all the same atoms, it's going to be not polar. Again, let's just look at the partial negatives and positives. Between carbon and hydrogen, hydrogen will always be positive, while the carbon will be partially negative. Again, to be polar, you need to have a positive end and a negative end. This does not have that. If we're looking at this over here, though, between the hydrogen and carbons, we have these polarities. However, the chlorines are going to be negative, having some other positives. So if we just said these cancel out, we again have a negative end and a positive end to the molecule. This is where we get the idea of polarity. Again, positive end and a negative end. Alright, so let's take a look at how polarity and these intermolecular forces show us about some of the particles that we see. So intermolecular forces are the forces between molecules, so between one molecule and another. These are not bonds. Okay? So here's a couple illustrations that we have. We have something like water. These attractive forces are indicated by the blue dotted lines. This is what they would look like if we talked about what's called the space filling model. But we can see that the negative side, the partially negative side, and the partially positive side, so that the red is attracted to the white in the molecules as we see in this space filling model. So what are called dipoles is this area of positive to negative between the bond. And as we've talked about and shown, we have partial negatives and partial positives, as we've shown. These together will indicate the idea of what's called the net dipole, in which way this is a polar molecule. As you know, water is a polar molecule. These are just general forms of if we had a polar molecule of what is attracting and what is repelling. So we see that there's a lot more attracting forces than repelling forces, which is why essentially a polar molecule is going to attract other polar molecules. Some examples were shown on the previous slide that we have up here that we've gone through. So HCl, water, this one here, this one here. So we have lots of examples, and we determine this being polar by looking at the partial negatives and positives, which is what you're going to need to do really to determine polarity, unless you can pick out its shape from its dot structure, which generally, by definition, you can't. So these are the forces between polar molecules. They're called dipole forces. Essentially, a dipole, something polar, and a dipole, something polar. So when we look at the types of intermolecular forces, this is the medium strength. Medium strength. A more specific type is what's called hydrogen bonding. This is a very specific dipole-dipole force in which nitrogen, oxygen, or fluorine, is connected to hydrogen, as shown with the example down here. So because we have hydrogen and oxygen here, this positive and this negative is almost, you could say, close to 1. It's very, very close to 1. The same would hold true with the negative of the negative of nitrogen and the positive of hydrogen. So this is also very close to 1, which means this attraction is very, very strong. And even though it's an attraction, as we see with the dotted lines, it's titled a hydrogen bond because it's an attraction so strong, it's very close to bonding itself. And this gives quite a big clarity when we talk about things being the attractive forces. So let's see how that plays out with the effects of attractive forces. So the ones with NH3, H2O, HF, those all have hydrogen bonding. The ones in yellow, very similar to those, all just have dipole-dipole forces. So when we look at the boiling points, hydrogen bonding boils at a much lower temperature, I should say much higher temperature, less negative is closer to 0, than pH 3. Even though phosphorus is heavier, its attractive forces are way weaker. Look at water. Water, lighter, boils at 161 degrees centigrade higher than H2S, which is heavier. Same for HF, hydrogen fluoride. Because of those hydrogen bonds, its attractive forces are way stronger than something like HCl. So those attractive forces can have a huge influence. All the ones in yellow are polar. As you can see, their values are generally much, much higher than the ones that are nonpolar. But the ones in red, hydrogen bonding, that makes a huge difference in attractive forces. So this is a very specific type of dipole-dipole force. Now the last one is London forces. This happens when you have a permanent dipole or a polar molecule makes a dipole and another one, and this will have a weak attraction. So when we have what's called a polar molecule, right here, comes close to a nonpolar molecule, the electrons are going to be repelled by the negative side. So the electrons are going to move away from the negative side of the dipole. That creates a slight positive, and this will create a slight attraction. Now it is very slight, but it is measurable, and that makes a big difference. Now London forces happens between all molecules. Keep that in mind, all molecules. But it's the only force between noble gases and nonpolar molecules. And when we take a look at that, if these are polar, look at the boiling points. The lower, the worse. The lower means the worse attraction. Even for something like hydrogen and oxygen and chlorine, we see that it increases as things go up. These are all nonpolar, but the heavier something is, the more attractive force there is. And even when we get to something like bromine, it's really heavy and actually has a pretty high boiling point for being nonpolar. CH4 is actually quite light if we look at its molar mass. That's why its attractive forces are so low. But then these are much heavier, so that's why the attractive force increases and we have more attraction to have a higher boiling point. The higher the boiling point, the higher the attractive force of those things, and that's why it increases with atomic mass, or you could say the number of electrons present in the molecule. And just one final comparison, even though something like HCl is polar and oxygen is nonpolar, they're about equal mass, pretty close. But you can see 183 to negative 185, negative 183 to negative 85, a very large difference for the idea of polar. When it's polar, it has a much higher attractive force, it takes more energy to separate those molecules, because essentially that's what boiling is a separation of a liquid to a gas. So to round up all of these attractive forces, most of them we've talked about. Remember, attractions are very weak. Students often get these confused or mixed together. If you list all the forces in Chapter 6 from strongest to weakest, ionic in general is the strongest. And then covalent attractions, which are bonds. Metallic can be in between the two because it depends on the metal. Then we get to the intermolecular forces down at the bottom. Hydrogen bonding, dipole-dipole, and then London dispersion forces. So bonding is much stronger than attractions. Please keep that in mind. Come in with any kind of questions, and I'll see you soon.